Hello students, welcome to today's lecture of fluid mechanics. So in the last class we were discussing about the properties of fluid. So we discussed about the density. We defined density as a mass per unit volume. This density is basically the mass density or the specific mass. It is the mass which the fluid possesses per unit volume. And we also discussed that the density of the fluid decreases with the increase in temperature and it increases with the increase of pressure, right? Then we discussed about the weight density and we defined it as the weight which the fluid possesses per unit volume, right? So this is also known as specific weight, and the weight density comes out to be equal to the mass density into the acceleration due to gravity, right? So this weight density will be depending on the gravitational force or the gravity, and it also depends on the temperature and pressure. So this weight density will be different at different places for any particular fluid, where the acceleration due to gravity will be varying, right? So a little more I would like to elaborate or discuss about this mass density. Basically in fluid mechanics, these heavy or light words serve to compare the density of one fluid with respect to another. For example, we know that mercury is heavier than water, then we say that water is heavier than oil. Similarly, we know that seawater is heavier than fresh water, and cold air is heavier than hot air, and so on. There are so many examples, right? Now, when two immiscible liquids, for example, such as oil and vinegar, are poured simultaneously into the same container, we know by experience that the lighter liquid will eventually settle on the top of the heavier liquid, right? So a practical example of this concept of mass density is a solar pond. So let me first draw this solar pond, then we will see what it is like. So in this solar pond, there is a bottom layer. These layers are thin enough. I'm just drawing them a bit large so that you can view it properly. So this is a layer of solid material, so I'll call it as a solid layer. Then on the top of that we have a thin layer of this salt water, right? So salt water is heavier than fresh water. So this will be salt water. And above this, we know there will be a thin layer of fresh water, right? So this is layer of fresh water, right? So this is basically a solar pond. So this is how the solar pond looks like, and as you can see from the figure that a solar pond consists of a layer of fresh water on the top of a layer of salt water, and as we know that we are talking about solar pond, so there will be sun rays that will be falling on it, right? So suppose we draw it like this, right? So these are the sun rays that are falling on the fresh water, right? So since the water layers are thin and most of the thermal energy from the sun passes through the water and is absorbed by the solid material below. And this raises the temperature of the solid, which in turn heats the salt water adjacent to the solid layer, right? And the presence of the fresh water surface layer insulates the heated salt water from the atmosphere, right? So the energy is stored in this salt water. Thermal energy is stored in this salt water, which can be extracted by just supplying some cold water, and it can be extracted as the warm water. So we supply the cold water and we'll get the warm water. So this is the cold water in, and we get the warm water at the outlet, right? So this thermal energy that is stored in the salt water layer can be extracted from it, and it can be used for space heating or other purposes, right? So this is an application of this property known as density, right? So another thing, if I ask you, is that what is the characteristic that determines the density of a gas? So in case of gases, what is the characteristics that determines the density? So the answer is basically the molecular weight. So it is the molecular weight that determines the density of a gas. Basically, what I mean to say is that the density of a gas at a given pressure and temperature is basically proportional to the molecular weight, right? And this can be easily shown by this table here, in which you can see that as the molecular weight is increasing, the density is also increasing from hydrogen to propane, right? So the density of the gas is basically directly proportional to its molecular weight, right? So this is what I wanted to just discuss. And one more thing I would like to highlight here is that if we see the density of hydrogen gas is nearly equal to 9 into 10 raised to power minus 5 gram per centimeter cube, and density of mercury is of order of 13.6 gram per centimeter cube. So if you just see the difference between the two values, there is a difference of more than 5 orders of magnitude, right? So this is a huge difference. Earlier we stated that the fluid density is related to pressure and temperature. And since flow conditions influence the pressure and temperature in a fluid, so they must also influence the fluid density, and this influence is basically taken care by the state equation, right? But this is not often important for liquids. So basically the state equation for a liquid reduces to the statement that density is constant. But for gases, the changes in the density induced by temperature and pressure can be significant and must be accounted for to correctly predict the behavior of a gas, right? So we'll investigate this common state equation for gases a bit later, but this is what I just wanted to discuss about this density.